Thank you. So yeah, this is Shapeless Party Tricks in the Enterprise. All these slides are on GitHub. This is kind of a long link, but if you go to github.com/cdubs, I have the repository pinned right now. So feel free to look at that. So yeah, today I'm going to give kind of a brief introduction to Shapeless, but not really because I don't have time. So mostly I'm going to dive into a couple examples of a couple methods I've written at work over the past few years. These are things that I've written at like Fortune 500 companies, and like Shapeless can be used in the real world. It is used, and I want people to know that. This isn't going to be an in-depth, not by any means an in-depth explanation of Shapeless or an introduction to it. There have been some great talks and blog posts and even a book about Shapeless, and so there's a resource slide, and I encourage you to check that out if you want some more information about that. The goal of this talk will be, if you haven't used Shapeless, to kind of pique your curiosity. If you have, maybe these are a couple ways of using Shapeless that you hadn't thought about using. So yeah, I'm Cody. I've been doing Scala development for quite a while now. I work with cats. I'm on a team that does machine learning and natural language processing at Salesforce. And I think it's worth calling out that when I first looked at Shapeless, I couldn't really wrap my head around it. It's fairly abstract, and I looked at it and I was like, I'm pretty sure it's doing some cool things. I just don't really know what they are. And it wasn't until like a year later, when I had a good concrete use case for it, that it started to click for me. So if you've looked at Shapeless or like watched a talk about it and couldn't wrap your head around it, don't worry, that's like a totally normal thing. Yeah, the Shapeless README says that it's a type class and dependent type-based generic programming library for Scala. Well, that's kind of abstract, and so yeah, like I said, I'm not going to really have time to go into some of the details of like how it's implemented, but I do want to show a few examples of using it, and I also want to point out that a lot of libraries in the Scala ecosystem are using Shapeless. Again, these are libraries that Fortune 500 companies are using. Like, Shapeless is not an academic experiment. I think some people think of it that way. Maybe it started out that way, but I think at this point it's a pretty key component of the Scala ecosystem. And these libraries tend to use Shapeless for like type class derivation, and it's really good for that. But today I'm going to focus on a couple kind of one-off methods where I think you can do some cool things with Shapeless that don't quite maybe fit that pattern as much. So first example is from my current team at work, where like a task that we would have is seeing an email, and maybe it looks like this: what's your availability on Wednesday afternoon? And trying to determine, is this person trying to schedule a meeting? And so in order to develop a model that does that, you need some training data. So we might have some judges read some anonymized versions of emails and label them like, hey, is this email talking about scheduling? And ideally, they would either all say yes or all say no. In practice, they don't always agree. Sometimes it's kind of ambiguous whether someone's scheduling a meeting or not. So one statistic that can be helpful for us to look at when we're kind of trying to assess the results of these labeling tasks is what's the pairwise agreement between labelers. You know, if we see that, hey, these two labelers are agreeing 95% of the time, but each of them only agrees with this other person 50% of the time, well then like not everyone has the same understanding of what it means to like schedule a meeting with someone or ask about availability. So we should just kind of, you know, talk that through and write up some guidelines, figure that out. So the first step to coming up with this pairwise agreement rates is to just get, you know, a collection of all the unique pairs of labelers. And so this is something that one of the members of my team, I think, had a pull request that looks something like this, where, you know, you take this list of elements and you just kind of break it into a list of tuples of all the unique pairs of those elements. So if our labelers are A, B, C, and D, then, you know, we'd get back A and B is one pair, A and C is one pair, et cetera, et cetera. Pretty straightforward. I think this implementation is actually based on this Stack Overflow post. But one of the other members of my team said, oh, hey, this is just combinations from the standard library. And so yeah, sure enough, if you look at combinations, if I call it with the number 2, then I'll get back all my pairs, A and B, A and C, et cetera, et cetera. And it's a little more flexible in that you can call it with you know, the integer 3 and get back the pairs of unique, well, I guess they're not pairs, triplets of unique combinations. So I thought, oh yeah, this is cool, this is more flexible. But then the original author pointed out, oh, well, this is actually a little awkward because this returns me like a list of lists. Whereas in mine, I really only care about pairwise agreement. So I was getting back a list of tuples. The list of lists is more awkward to work with because I know there should be exactly 2 elements in that list, but like, how do I prove that? And that's not really the type safety that we'd want as Scala developers. So yeah, the original person who had suggested combinations was like, oh yeah, good point, as you were. But I kind of was thinking, can we do better than this? Can we have like the best of both worlds where we can say whether we want groups of 2 or groups of 3 or whatever, but not have to give up that type safety? And that might sound like a little far-fetched, right? Because we don't know whether this person is going to say 2 or 3 or 20. So how are we going to do better than returning a list or seek or something like that? Well, it's possible, maybe. I mean, it's conceivable, because it turns out that the compiler actually, for literal values, has kind of special handling, gives those special types. And you can see this if you create final vals. So if I create a final val and assign it to some runtime integer value, like available processors, then sure, I just get back an int. But if I assign it to a literal, like 3, I get back an int, but it's this refined int type, where it's furthermore the int 3. And the compiler does actually keep track of that information. And Shapeless actually provides a way for you to take advantage of that and use that to do some cool things. So I crafted up this little concoction. This will look a little messy to you, especially if you haven't used Shapeless, maybe even if you have used Shapeless. But I want to point out that, this first part here is just like type parameters. So there's not like anything particularly interesting right in here. And they're actually a little more complicated than they need to be. That's been changed and will be in the next Shapeless pull request. But basically, it's taking a natural number, which is basically like an int, but we keep this kind of literal value of which int it was, and your list of items. Then it's just taking some implicit arguments, so just some type class instances. Nothing too fancy there, really, other than some maybe awkward types. And then it's just calling through to the standard libraries combinations and kind of running that through a transformation. This get or else is, OK, that's a little clunky. But this is just if we tell the standard library, hey, I want groups of 3, and for some reason it passes us back a group of 5, we kind of have to handle that. And I don't really want to return an option because I know the standard library is not actually going to do that. So I just, YOLO, throw an error. So OK, there's like maybe some kind of type noise in here. But if you look at it, like this is really just a one-liner, I think, when you kind of ignore the cruft. And if you call it, you can see we call combos with 2. We get back the list of all the unique pairs like we would expect. If you call it with 3, then you get back the triplets. But the cool thing is, check out the return types. So when we called in 2, we got a list of a tuple 2 of strings. And since these are REPL results, kind of the distinction between compile time and runtime is a little blurred. But I can assure you that like the static compile time return type of this is a list of tuple 2. And when you pass in 3, it's a list of tuple 3. And we can do this because Shapeless is keeping track of this literal information. I might be close on time. Can I come back? So yeah, and we pass in 4, we get back a tuple 4. And so to me, I think this is kind of cool because we had, a 1 to 3 liner, depending on how generous you are, that gave us the both of best worlds. We can use different integers, but we can still retain all that type safety that we'd want. So a use case that came up at a previous job, we had a client and a server that spoke via WebSocket protocol. And we had an API on the server where you can say, OK, now I just want to asynchronously await a message from the client. And so for the purpose of this demonstration, I'm just going to say awaiting a message is where you just like sleep for a millisecond and then return some random message. In this case, I'll just do the current time millis. So this is just some IO of string where the string is the message, and we can run it. But then some time passed, you got into states where, okay, well, I want to wait for 2 messages from the client, and I need to do something once I have both of those results. Okay, well, that's easy enough with us. We can do a for comprehension, or there are a couple ways to do this, but if we're working with I/O, right, we can just do this and then return a tuple of the 2 messages. And we get back our I/O of our tuple 2, and you can see we can await 2 messages. Sure enough, some time passed, and turns out, oh, well, when we get into this one state, we actually need to await 3 messages from the client, because then we're going to do some stuff. And so, okay, you can throw another line in the for comprehension. Or if you're using cats, like there's even some other syntax that's pretty nice. Like this is still pretty concise, especially maybe the second example. But this is the time that my coworker at the time, Randy, who's actually sitting over here, hi Randy, he came to me and he said, you know, there's clearly a pattern here. And he had the intuition that Shapeless might be able to do this nicely. And I thought that was a really great idea. But before I dove into the Shapeless, I also kind of recognized, oh, this looks like ReplicateA. We call it in cats. I think it's ReplicateM in Haskell. Where basically you take some applicative functor and you repeat its effect n times. So here, like, we can take our await message, we can replicate it twice, and we get back these 2 messages. We can replicate it 3 times, we get back these 3 messages. But it's kind of like in combos before, where we know we're expecting exactly 2 or exactly 3, but we get back this like list, right? So yeah, I think we agreed we could do better, and we wrote up a more general version of this that preserved the type safety. So this became ReplicateH, which is actually lives in kittens now. If we have time, I'll come back to the implementation, but I want to show some examples of using it. So if we take our same await message and replicate this twice with ReplicateH, then we still get back those 2 messages, but you can see the result type is an I/O of a tuple 2 of string. And similarly with 3, tuple 3 of string. It's a similar pattern to before, right? The one difference here is that the combos method that we wrote was just calling through to combinations in the standard library and kind of doing some stuff with the result. It was pretty specific to that use case. This ReplicateH is actually really general. This will work with any applicative functor, and it turns out there are tons of applicative functors. So I don't know, we did it with I/O. That's cool. What else can we throw at it? Let's throw a list at it. So if we have a list of the elements 1 and 2, we replicate it twice. What does that do? Well, it gives us back the pairs of 2 element pairs. It returns all of those. This is different. It looks extremely similar to combinations, right? But the difference is it'll pair items with themselves. So we get 1 paired with 1. Which didn't make sense for us when we were talking about labelers, because every label is going to have 100% agreement rate with themselves. That's not very interesting. But this is just when you turn it through the crank, this is what ReplicateH does on a list. And yeah, similarly, if you give it 3, you just get back the triplets of elements, right? OK, what other applicative functors can we throw at this? Let's try out state. So this state here will have some integer state value. We're going to take it, we're going to return what that int was, and we're going to say, all right, our new state is now just whatever it was plus 1. And so here, I'm not doing anything with ReplicateA or ReplicateH or anything yet, but you can just say this is just basic state operations. If I run it with 0, I'll get back, OK, well, your new state is 1, and the value that I returned is 0. Let's throw ReplicateH at it. So I have a few different states here where all I'm doing is changing this from 2 to 3 to 4 here, right? And there's a corresponding change in the result type from a tuple 2 to a tuple 3 to a tuple 4. And when we run them, you can see that when we run the one that replicates the effect twice, then sure, our output state ends up being 2 because we've incremented twice. Along the way, it shows you here are the values that I saw while I was doing this. The first time it returned 0, the second time it returned 1. and it just collects these into our tuple 2 in this case, our tuple 3 in this case, and our tuple 4 in this case. And as you would expect, if I replicate the effect of this 4 times, my final state ends up being 4. Let's just keep throwing some more stuff at it. So Rob, sitting over here, has this auto library, a parsing library. And so it has letter, which is a parser for a single character. And he has a combinator in there called many-n, where you can say, hey, I want to repeat this parser 3 times. So yeah, if you throw like ABC at it, you can see it does pull back ABC. Similar to the pattern we saw before, we're getting back a list, even though we know we expect exactly 3 of these things. He has some other syntax where you can use this little squiggly operator. And so you can do, letter squiggly, letter. And that works, and it has a nice type safety. It returns back this nested tuple, which depending on your use case might be fine or might be a little bit awkward. But I think it's cool to see that ReplicateH also just works pretty nicely here. Let's take this, parser for a character, replicate it 3 times. Now we have a parser that when we run on our string, we get back a tuple 3 of the 3 characters that it parsed. Let's see, I think I might have enough time to take a brief glance at ReplicateH implementation. Let's see, oh yeah, it's not there. I need to put it on my other screen. Okay, that's really small, isn't it? Okay, so this is ReplicateH. The whole file is 38 lines long, which isn't trivial, but it's actually not terrible for something that's this general, I think, and does this many different types of things. And if you've used Shapeless before, you start to kind of filter out a lot of this mentally as boilerplate, right? So like, oh, here's my actual type class. This is some aux pattern stuff. Then ignore that. Here are the 2 type class instances that I actually need to be able to do this. And then really the only logic is like right here. I just call through to the 2 type classes one after another, and it replicates this thing in the way that I want. So I don't expect anybody here who doesn't already know how Shapeless works to see this, but what I want to point out is just that, it's a lot of white space, a lot of types, but like the actual implementation of this is fairly trivial once you ignore that stuff. I think it's like this little call one thing and then call the other thing. And so like if you think this is interesting, check it out more. I think learn more about Shapeless. This is just kind of whet your appetite. Okay, so can I get you back to the other screen? That's the question. All right, computers are hard. So I really just have like takeaway lessons on another slide. So yeah, maybe I can. The problem is my terminal got into full screen mode, I think. Hey, yeah, okay. All right, computers. So, all right. So my takeaway lessons really are just, one is that if you're like, oh, Shapeless is cool, I want to use it, but you don't have a concrete use case, I think it might actually be kind of hard to wrap your head around. It was for me. If you can do that, that's great. But I would say viewing it through some concrete lens is kind of the easiest way to learn it. So when is it that you would want to use it? So if you know something at compile time, and you're telling the compiler, like, I know this, but it doesn't know that, then that's often a time when like you can use Shapeless to kind of get some of that compile time information known by the compiler. And yeah, like there might be these implicits and these type parameters that get kind of noisy, but I think the actual implementations are often like very little logic, just kind of a lot of typey, instancy boilerplate. Yeah, so thanks to all these people. I'm running low on time, so I think we have a little time for questions.
How how about the compilation time when you started using Shapeless massively? What happened to the compilation time?
Yes, so this can be an issue. Compile times can go up significantly. In practice, it hasn't been a problem for me. I have seen it be a problem for some people. I'm eyeing someone in the front row here. If you try to completely use coproducts instead of kind of the standard way to do sum types in your code base, everywhere, then okay, it can add up to some really big compile times. If you use it for this sort of thing here and there, in my experience, it's been all right. We use Doobie all over the place, which is using this sort of stuff for some derivation, and it's not bad.
I just want to add. That's a really good question, and Cody might be eyeing me in the front row with respect to this question. I did a lot of work with Shapeless at Verizon, and I'm happy to say that Miles' inductive implicits patch to the compiler helps in virtually all the cases that were causing, in my particular case, multi-hour compile times.
Anything else? Oh yeah, set that.
One of these methods, like the combinations method that you showed that it expects a literal int. If I pass it something that isn't a literal int, does it fail to compile, or do I just get a more general type back?
Yeah, I think with this implementation, it would fail to compile. It would probably, I don't know whether it's desirable. I would imagine it's probably possible to write one that kind of gracefully falls back to giving back a list or something, but I don't know if that's really good, better or worse behavior.
So for comprehension, you were using flat map, so it's monetic, type of thing, but then you mentioned that it only works for replicative functors. So is there a thing that you use the results of the previous monetic replication, replicate from monads, like map accumulation strings?
Yeah, let me think about that. I'm not quite sure. I would have to think about what the non-type level version of that looks like. Is that a fold M maybe or something? And I would imagine that if you can do it in kind of the non-type level way, non-type level programming way, then you could do it with Shapeless probably. But I don't know. That's something I have to look at and try out.
Great. Any more questions?
One of the things that you showed up there was when you created an int that had the value of 3. You said that it was the compiler stored that int literal. Was that because of the JVM integer caching? It knows that's a specific pre-created integer? And if that's the case, does that mean that any number over 256 would not be stored?
So sorry, I've been forgetting to repeat the questions. But yeah, the question is basically when it knew that this int literal was specifically the int literal 3, is that because of the JVM int caching? No, this is not related to that. This is all in the Scala compiler, and it parses your file and it sees, it builds up the AST and it sees oh, here they provided a literal int value, and it stores some extra information about what that was.
One last question. So is it only about int literals, or is it generally about compile time constants? So if I had a literal 3+4 or another function, maybe that has really only compile time static information of label file or whatever.
Yep. Okay, so the question was basically, is this specific to int literals, or is it kind of any static compile time expression, if I had 3 plus 4? So there are probably other people in the room who could answer this better than I can, but I don't think 3 plus 4 is something that has that it knows that static compile time is 7, but it does know if just for any any primitive, and I think also strings and symbols, but I think those are going away maybe. So yeah, those are, and the string literals is something that Shapeless actually uses quite a bit to represent case classes in a more generic form where you have kind of a literal symbol that's the field name.
Great. That's all the time we have for questions and answers. So please grab Cody to that conference.
Thank you.